Hello everyone, thank you for being here today. I'm Xuan and my teammate Xiaodi. Our project focuses on predicting housing prices using real estate sales data from Connecticut. We started with a raw dataset from data government, cleaned and transformed it, explored meaningful patterns through EDA, and then built and evaluated several regression models, ultimately improving our prediction accuracy using XGBoost. We also created a user interface web to help users filter and explore home listings based on the data. Today, we will walk you through our process, findings, and what we learned along the way. In this project, we analyzed the real estate sales data from Connecticut to better understand what factors affect home prices. The dataset covers over 170,000 transactions from 2002 to 2022 and includes assessed value, sale prices, property types, and geographic coordinates. We divided into 3 steps. The first one, the EDA, clean the datasets, remove the missing values, explore distribution of sale amounts, property type, and residential type. And we built a regression model, evaluate performance using mean absolute error, root mean square error, and R squared. Then we filtered dataset to improve the model accuracy. And the last one, we built a simple user interface for home buyers. Let's have a quick look at how our dataset looks like. I took 5 unique values for each column. The key features list year, data recorded, sale amount, assessed value, sale ratio, property type, time, location, and year listed. We removed rows with missing value and split location column into latitude and longitude. Here is all the numerical data. Our goal is to predict house prices in Connecticut using regression techniques. We could see the data info include 70,000 records and 5 features. The time range is from 2006 to 2021. And the feature selection and pre-processing time. We dropped irrelevant and redundant columns. For example, data recorded since the listing year is enough. Actual sale dates not needed. And address also redundant since time, latitude, longitude already capture location. For ratio, we already have sale amount as target, and we use assessed value to do the prediction. Assessor remarks and OPM remarks, also irrelevant notes. And then we did one hot encoded to categorical column, time, property type, and residential type. We split 80% data for training, 20% for testing. And here's our 2 visualization for the EDA. The first one, histogram, the distribution of the sale amounts. We could see most homes sell below 1 million, with a long tail of few very expensive outliers. And box plots, the sale amounts by property type. We could see the residential properties show the widest price range, including the most extreme high-value sales. And then move on to our model comparison and adjustments. I will share the first model we built. For the initial model, we used linear regression, include time as a location feature. The results here, we could see very poor performance, high error, low explanatory power. And then we use XGBoost. We drop time since we have more granular features, latitude and longitude. We could see a significantly improved performance by cleaning the dataset and replacing the coarse ton feature with more precise latitude and longitude. I think because most of them are hard to capture using simple models like linear regression. And now my teammate Xiaodi will show how we refine our method.
Okay, so to further improve our model, we applied filters to remove outliers and unrealistic records. We excluded properties with sale or assessed values over 1 million and filtered out entries with extreme sale to assessment ratios. This targeted filtering removed less than 2% of the data, but helped reduce skew and enhance model stability. It made a notable difference by ensuring that our model focused on typical transactions rather than outliers, leading to more generalizable results. Here you can see the final metrics after refining both the model and the dataset. XGBoost achieved an R-square of 0.826 and an RMSE of just 83,000, far better than the linear model's R-square of 0.752 and RMSE of over 91,000. This means XGBoost not only fits the data better, but also produces more accurate predictions overall. This model became our final choice due to its consistency across multiple evaluation metrics. With our clean dataset, the final XGBoost model achieved an RMSE of 76,310 and an MAE of about 50K. That means on average, our predictions are within 76K of the actual sale price, a very reasonable error considering that the average home price in our dataset is around 400K. Also, with an R-square of 0.826, our model explains approximately 83% of the variance in home prices. We also examined feature importance based on the number of splits in the XGBoost model. Latitude and longitude came out as the most important features, even more predictive than assessed value. This reinforced our decision to use exact geographic coordinates instead of town names. Assessed value and listing year still play strong roles, but were secondary to location precision. To make our result more accessible, we built a web UI that allows users to input features like assessed value, year, latitude, and longitude. The UI runs our trained XGBoost model in the background and outputs a predicted sale price. This makes the tool user-friendly and practical, especially for prospective buyers or agents who want a quick, data-driven estimate without needing to write any code. Now, I'll show the demo for our project. As here you can see, we have already a property input and the assessed value, the sale year here. Wait a minute. The sale year here, the longitude and the latitude. User can just input their own value here and just click the predict sale prices, and they can like predict their houses value. So for example, if we have a house has a assessed value like say 300K, okay, 300K, and who sold at 2022, and we have a longitude, say since we are in Connecticut, it's -71 to -73, and the latitude is from 41 to 42. So let's say the longitude make it 71.745, and the latitude we just make it 41.567. Okay. Then by clicking the predict sale price, we will have the estimated sale price on 2022 is around 526K. So if you have a assessed value, like say we still have like 300K, and the house owner want to sell it on 2026, we can also predict like how much this house valued. As you can see, it will be probably 750K for this house selling on 2026. So yeah, this is basically our project. Our references include the Connecticut real estate sales data set and foundational XGBoost paper by Chen and Gustrin. Thank you for your attention. We're happy to take any questions.